Today we're going to talk about elementary particles and the standard model of the atom, or as Enrico Fermi would say, if I could remember the names of all these particles, I'd be a botanist. And it's important to note here that this lecture is not going to answer all of your questions about the standard model or elementary particles. In fact, you're probably going to leave this lecture with more questions than you began with. Enrico Fermi once said, "Before coming to your lecture, I was confused on this subject. After having listened to your lecture, I'm still confused, but on a higher level." And that's where we'll be at the end of this. You'll feel better about the topic, you'll be more knowledgeable about the topic, so that you'll be able to ask better, more intelligent questions about everything we're going to talk about today. So let's talk about something that you should already know about: the development of our knowledge of the structure of the atom. Prior to the mid-1800s, we had scientists like Dalton who said that the atom was uniform and indivisible. And then in the late 1800s, J.J. Thomson came along with his cathode ray tube experiment and actually discovered that you could extract cathode rays from the atom. And these negatively charged cathode rays are what we now know to be the electron. Ernest Rutherford in the early 1900s came along and said, I want to prove J.J. Thomson's plum pudding model of the atom, which was the idea that the atom is basically uniform goo filled with negative chunks in it. So again, uniform in composition, but not indivisible as Dalton thought. To accomplish this, Rutherford did his gold foil experiment, where he basically took photo film and an alpha particle shooter, and he fired off alpha particles at a piece of gold leaf or gold foil, hence the gold foil experiment. When he fired these alpha particles off at this piece of gold leaf, what he expected was that if the atom is in fact uniform with goo and negative chunks in it, then the majority of these particles should go straight through, like firing a machine gun at a wall of Jell-O. Everything should go straight through, regardless of if you have yummy little fruit chunks in it. So it turned out that this was mostly correct. Most of the particles did go through, but some of them deflected off. Enough of them deflected off and in strange directions that this could not be ignored. And this eventually led Rutherford to state the nuclear model of the atom, which was that the atom is basically neutral, but it has a dense positive core at its middle. How did he come to that conclusion that the core was dense? Well, dense is because the majority of the particles went straight through, but then they occasionally hit something that deflected particles in the wrong direction. That must mean that we are hitting a small but heavy enough to move other particles out of the way obstacle. But small because most things pass through, again, but very heavily packed, very dense, because it was able to push these particles out of the way. Why was it positive though? He theorized that since he was shooting positive particles at this atom, if the nucleus had been negative, then the positive particles simply would have attracted in and stuck, and he never would have seen the deflection at all, and we would have continued to believe the plum pudding model of the atom. But in fact, they deflected off, which indicated to him that particles were coming in and rebounding right back, or deflecting out of the way. That in fact, this dense nucleus was moving the path of the particles around it so that they could continue on their way. So the nucleus is dense and it's positive because it deflected positive particles off of it, yet it allowed the majority of things to pass through. So in Rutherford's model, we have this dense nucleus that makes up the majority of the mass of the atom, but we have this sparse electron cloud that neutralizes the atom and takes up most of the space in the atom. Then along came Niels Bohr, and we saw some of what Niels Bohr's work was last week when we did interference and diffraction, when we looked at hydrogen gas and we put it under pressure and electricity, and we could see distinct red, teal, and purple lines being emitted by the hydrogen lamp. These indicated that there are, in fact, not a cloud of electrons, at the center of the atom, but instead organized electrons, discrete energy levels, where electrons can jump up and jump back down. And when an electron jumps up, it's given energy. And when an electron jumps back down, it gives off energy in the form of light. This became known as the planetary model of the atom, and it's still the one that we pretty much use today. We can talk a little bit about probability clouds and things like that, but we'll wait until Thursday for that. We've already discussed that there are 4 fundamental forces that govern all of nature. If you might recall, they are the strong nuclear force, which acts over basically the nucleus of the atom and actually binds the nucleus together, right? Because why would protons and protons hang out together, right? They should naturally repel each other, and yet they don't. Why is that? In the nucleus of the atom, there is this much stronger, more overwhelming force happening, and that is the strong nuclear force. That is literally why it's called the strong nuclear force, because it is stronger than anything else and can force those electrons together. We also have the weak nuclear force, which acts over also very tiny distances, about the diameter of the atom, and is responsible for nuclear decay. Then we have the electromagnetic force, which acts over significantly larger distances, as we have in fact seen lightning pass from the sky to the ground. And it's responsible for a whole lot of things that we deal with in our everyday lives. And then finally, we have the gravitational force, which is the weakest of these 4 forces, yet acts over the largest distance. These 4 fundamental forces actually govern a lot of what we see going on in the atom, from binding the nucleus together to the way atoms bond and all kinds of things. So these 4 fundamental forces are really very important. But since we started trying to unify these 4 fundamental forces, something interesting has started to happen. We keep discovering more particles. Now, in the beginning, we saw the electron discovered in the late 1800s, and it was years before we finally came to the discovery of the proton, and then later the neutron. And then all of a sudden, something happened in the 30s and 40s. We started to see an explosion of particles leading up to the 60s, where there were multiple particles being discovered all the time. Kaons and pions and, Q mesons, and I think I just made that last one up. But anyway, we saw tons of particles. And every time we discovered something new, somebody came running in saying, I just discovered the smallest particle. I just discovered the most fundamental building block of nature. And it kept on getting more and more and more complicated, right? And so this is where Fermi's statement comes in, that if I could remember the names of all these particles, I'd be a botanist. So things started to get pretty complicated pretty quickly. So let's talk about these particles and the categories that they fall into, because what we've learned so far is that when science seems like it's getting too complicated, there's probably a simpler structure to organize it all. Let's start with the leptons. Leptons are fundamental particles that have no internal structure. The one that we are most familiar with is the electron, but there are in fact 2 other flavors of leptons that we are not as familiar with. They are the muon and the tau. And if we look at that chart, we can see that they are increasing in mass as we go from the electron to the tau. There's also something worth noting here. They all have a charge of -1. There's another type of there's another type of lepton called a neutrino. It turns out that every one of these leptons, the electron, the muon, and the tau, come with their own type of neutrino. So we have an electron neutrino, a muon neutrino, and a tau neutrino. Now, let's take a moment to talk about that mass. That is a unique unit, mass, in mega electron volts per c squared. So let's take a moment to talk about that. Einstein's equation, E = mc squared, is groundbreaking for more than one reason. What it means is that mass moving near the speed of light can in fact become energy. We can already kind of tell from the units and what we know about kinetic energy that if we take an energy and we divide it by a speed squared, we will get kilograms out of it. But what it means here is that the mass of an electron is its energy divided by the speed of light squared. Remember, that's the speed of light 3 times 10 to the 8th squared. Okay, so what's an electron volt or a mega electron volt? What is that unit? We know that 1 volt is 1 joule per coulomb. So what is an electron volt? An electron volt is 1.6 times 10 to the negative 19th coulombs times 1 volt. We can see that if we multiply 1.6 times 10 to the negative 19th coulombs by a joule per coulomb, our coulombs will cancel, and we will in fact get an electron volt as what I like to call an electron's worth of joules. So a mega electron volt would simply be 1,000,000 electron volts, right? Mega is 10 to the 6th. So a mega electron volt is 1.6 times 10 to the negative 13th joules. So how do we get to that 0.511 mega electron volts per C squared for an electron? You take a mega electron volt, divide it by the speed of light squared, and multiply it by that 0.511, and you will in fact get the mass of an electron in kilograms. So this is simply a different way to look at mass, just a different unit, the same way we talk about mass in terms of kilograms and rarely slugs, or weight in terms of newtons and pounds. It's just a different unit to look at the same thing. Now you might notice some nuclear equations down at the bottom of that slide. What are those nuclear equations? Let's first start by breaking down a nuclear equation. In chemistry, you're used to counting how many oxygens are on one side versus how many oxygens end up on the other side. You're looking to conserve the atoms that are present. In a nuclear equation, there are a few things that need to be conserved. First thing that needs to be conserved is mass. The second thing that needs to be conserved is charge. The third thing that needs to be conserved is energy, because of course, energy always needs to be conserved, right? So in the nuclear equation that you see at the bottom of this slide, what you're looking at is a neutron decaying into a proton. The top row of numbers is going to be your mass in atomic mass units. The bottom row of numbers is going to be your nuclear charge. And I should have made that a 0. Sorry about that. I got carried away. So the bottom number there is charge. So as we see, we go over here and we see mass of 1 becomes a mass of 1. Charge of 0 becomes a charge of 1. So what must be coming out on the other side there? Well, hopefully something that has a charge of -1. But no mass, because our mass has all made it through. What do we know of that has virtually no mass in comparison to the size of a proton? Protons are typically about 2,000 times more massive than electrons. Actually, almost always 2,000 times more massive. We see an electron. So a neutron is able to decay into a proton or a hydrogen nucleus and an electron. We'll discuss some of the intricacies of that in a little bit. It turns out that this doesn't completely conserve energy, so there's actually another particle that comes out of here that has no mass and no charge, but has kinetic energy, and that is an electron antineutrino. There's a line there, that means anti. We are not ready to talk just yet about what an antiparticle is, but I want to let you know that whenever we see a lepton emerge, we see an anti-lepton come with it. Again, we'll talk about that more later in the talk. Just be patient. So now, let's talk about quarks. Quarks are fundamental particles that are known for making nucleons. What's a nucleon? It's a particle in the nucleus. Big shock, right? Positive proton, neutral neutron. Nucleon would be a nuclear nucleon, right? So quarks make up nucleons. And if you look at that chart, you see again these particles that you're familiar with. Many of you have heard of the up and down quarks, but there are also 2 more categories of paired quarks that we are not as familiar with, both increasing in mass. We have charm and strange because the opposite of charming is strange. And we have top and bottom. They were named for something in a book called Three Quarks for Muster Mark or something like that. You can ask Craig about it sometime. He knows about it. He tells me every year and I forget every year. I feel like a terrible human being for it. Anyway, you might also notice those charges, plus 2/3, negative 1/3. But wait a minute. Didn't Millikan figure out that charge is quantized? It comes in chunks of plus or minus 1. You can only have charge in plus or minus the charge of an electron. Plus or minus 50, the charge of an electron. Plus or minus 100, the charge of an electron. But not plus or minus a fraction of an electron. So what in the world is happening here? That's really upsetting. Well, it turns out that quarks only occur in nature in pairs or triples where they combine to create a charge of plus or minus 1. So quark triples are called baryons, and these are your protons and your neutrons. And quark pairs are called mesons. They're typically quark anti-quark pairs. Again, there's that word anti again that we're going to have to talk about at some point. I'd like to point out that the top quark was discovered here at the University of Pennsylvania, or at least its mass was detected using detectors that were machined at the University of Pennsylvania. We are pretty proud of that fact. Quarks and leptons fall into a category that we call fermions. There are 3 generations of fermions, as you have already seen, and the ones that we are the most familiar with that make up the matter that we are used to interacting with is actually, that's the lightest form of fermions. The next level of fermions is called generation 2 and then generation 3. Again, you can read that chart. I'm not stressed about whether or not you'll be able to figure out how that chart breaks down. But the next thing I want you to see is how these things combine. You to take a look at is a chart of common baryons, triple quark combinations. We have our proton on there, which is an up quark, and a down quark. What does that mean? That is plus 2/3, plus 2/3, minus 1/3. What does that add up to? It adds up to 1. Charge comes in chunks of 1, right? Plus or minus the charge on an electron. We also have the neutron in there, which is a down, down, up. So the 2 negative thirds cancel with the positive 2/3. But even though generation 2 and generation 3 are particles or fermions that we don't commonly interact with in nature, we do actually find their combinations out there. For example, the omega minus. It is actually a triple strange combination with a charge of negative 1. The next slide I want you to look at is mesons, which are quark anti-quark pairs. And what I want you to find interesting about this is the pion and the rho meson. They are both up anti-down particles. But look at their masses. Look at how dramatically different their masses are. The rho meson is actually 5 times more massive than the pion. So there's something more going on there with these particles that's allowing them to come together. Finally, antimatter. Let's take a moment to talk about what antimatter is. Antimatter is basically a mirror image of matter. It's kind of like the bizarro of matter. So there's such a thing out there as an antiproton. It is not just a negative proton, but if a proton is made up of an up, up, down, then an antiproton is made up of an anti-up, an anti-up, and an anti-down. You can't just put together some other combination of particles and expect it to be an antiproton. An example, a triple down would be a total charge of negative 1, and it might even have a similar mass to a proton, but it's not an antiproton. So antiparticles have the exact same mass as their particle, as their paired particle, but they have completely opposite charge. So what's interesting about this is that there's also an antineutron. That, if a regular neutron is a down, down, up, an antineutron is an anti-down, an anti-down, and an anti-up. It has the exact same mass as a neutron and is in fact still neutral. But fundamentally, the makeup of the charge is different. It's made out of different particles. And so it is in fact an antineutron, not just another neutron. And that's what's one of the important things about antimatter. So now let's go back a little bit and talk about some of these particles. Here's where it gets interesting. One of the things that we know about antimatter is that when it interacts with its regular matter self, it annihilates itself. So if I took a proton and an antiproton and I collided them into each other, they should in fact become pure light at such a high energy that we're talking the gamma radiation range of particles, of light. But look down here at the eta C meson. It's a charm anti-charm pair. Has no charge as expected. It's pretty massive, I must say. It is almost 3 giga electron volts per c squared, but it doesn't annihilate itself. Something interesting is going on here in the fundamental structure of these particles that is worth asking a particle physicist about. So I know that antimatter might seem like science fiction. Matter, antimatter particles. It seems like an episode of Star Trek. Captain, the antimatter containment chamber is falling apart, you know, but what happens on the Starship Enterprise if the antimatter containment field falls apart? We have annihilation with a lot of red shirts floating out in space. Seems like a problem. But it turns out that this isn't just science fiction. We actually use antimatter in medicine. A PET scanner, a positron emission tomography scanner, is actually a device that uses the annihilation of matter and antimatter to detect anomalies in the body. What it does is it utilizes a radioactive tracer, typically a beta positron emitter, so something that's emitting anti-electrons, and it sends it into the body. As this tracer travels through the body, typically in a compound that is akin to sugar, so it will travel through the bloodstream the way sugar does. We can then flood the body with electrons, high energy electrons, such that when they collide with these beta positrons that are being emitted by the tracer, we can actually find where these positrons and electrons annihilate each other. This helps us to find tumors, brain bleeds. It allows us to track seizure activity and a whole variety of other medical conditions. So antimatter isn't just science fiction, it's actually medical science. And who is it that first proposed the idea that antimatter could exist? Paul Dirac. He was actually working on a version of quantum mechanics that would be consistent with relativity, and he proposed that antimatter had to exist in order for this to work out. And it turns out that he was right. It was actually Carl Anderson who first observed the positron in a cloud chamber. So we've talked about the fermions. We have to now talk about particles known as force carriers. So in the electric fields lab, we worked on looking at equipotential lines and determining the electric field between charged particles, charged plates, things of the like. It turns out that the 4 fundamental forces of nature are field forces. They do not require contact in order to be felt. They in fact act via a field, or what some would define as an aura that emanates through space. How do they do this? How do they transmit their field to other particles in the field so that their presence can be known? They use these force carriers. The force carriers are gluons for the strong nuclear force, literally the glue that holds the nucleus together. That's why they're called gluons. Bosons, usually called W and B bosons, are responsible for the weak nuclear force and thus radioactive decay. Photons, or light particles, are what are responsible for the electromagnetic force, which if you consider that, the photon is an electromagnetic wave. And then we have the graviton. The graviton is a theoretical particle that is believed to be responsible for the presence of gravity and why we feel gravity. This is not to be confused with the Higgs boson, which is responsible for mass. A good way to think about force carriers and bosons is to think of them as messenger particles between particles in a field. So if you can picture two people on ice skates tossing a ball back and forth, as one person tosses the heavy ball, they skate backwards. As the other person catches the heavy ball, they also end up flying backwards, and so on and so forth as they transmit this particle back and forth. In this particular case, it's easiest to visualize repulsion with this because the two people are moving apart. But this is the basic idea behind the theory of how bosons and force carrier particles work, is as messenger particles traveling between other particles in a field. So what's one of the other things that I'd like you to take note of with these bosons? I'd like you to take note of references to phrases like spin and color. Fundamental particles are things that we are still working on figuring out all of the intricacies behind. And so what we do an awful lot is we talk about analogies that have conditions that make sense to us. You might already be familiar with the term spin in talking about electrons and talking about the quantum numbers that define an electron. In the Pauli exclusion principle, Pauli states that no two electrons in an atom can have the same set of quantum numbers. And what that means is that if we were to look at an element and how its electrons fill into its shell, we would see that first, electrons fill in facing one direction, and then they fill in facing in another direction. And I want to put quotes around facing in a direction because this concept of spin is really an analogy for saying that electrons in this atom, in this particular behavior, have two states. They can be spinning +1 or -1. It's not a reference to clockwise or counterclockwise or electric charge. Simply that once we have an electron in each of these seats, then an electron will fill in with this property that we're having difficulty describing going the other way. At the time, spin seemed like a good word because you could spin one way or you could spin the other way. And so it was an easy way to talk about electrons, that we had this binary property that we were dealing with. So like spin, there's another property to charge that we've had difficulty defining, but instead of coming in two binary states like spin, it comes in 3 states. And what physicists decided to call that was color. The rods and cones in the eyes can pick up red, blue, and green color. So what we say about how quarks come together is that when we have a quark triple or a baryon, we see a red quark, a green quark, and a blue quark. And that is one of the things that kind of neutralizes each other in the atom or in a baryon. Richard Feynman called his colleagues idiot physicists for calling it color, feeling that it would confuse the issue, and it does for many people, especially when we get into antimatter. If we see color in red, green, and blue, we print color in cyan, magenta, and yellow. And so when we talk about antiquarks coming together, we actually talk about them coming together with cyan, magenta, and yellow color instead. But color charge is simply another term to help us try to understand a property that instead of coming like spin in binary conditions, it actually has 3 conditions that relate to it. So a quote from Sir Isaac Newton: "Have not the small particles of bodies certain powers, virtues, or forces by which they can act at a distance? For it is well known that bodies act upon one another by the attractions of gravity, magnetism, and electricity, and these instances show the tenor and course of nature, and make it not improbable that there be more attractive powers than these. The attractions of gravity, magnetism, and electricity reach to very sensible distances, and so have been observed by vulgar eyes, and there may be others which reach to so small distances as hitherto escape observation." What was Isaac Newton talking about here? He was actually postulating the idea of other fundamental forces of nature. he was noting that gravity and electricity and magnetism, which at the time he believed were two separate forces, are able to be observed because our eyes can see them. But now particle physics is going beyond what our eyes can see. So where are we going now? One of the first places that we're going to is a grand unified field theory. So we have been able to, at high speeds in particle accelerators, been able to unify the strong nuclear force, the weak nuclear force, and the electromagnetic force. Gravity is still elusive to us though, and yet look at the math for a gravitational force and electric force. They are incredibly similar equations, inverse square laws, multiplying the quality of those two particles in the field. With electromagnetism, it's multiplying charges. With gravitational force, it's multiplying masses. These act very similarly. The math is almost identical. And yet we're having difficulty unifying gravity with the other three fundamental forces. So that's one of the things that we're looking for, is the theorized graviton, and trying to find a way to unify the four fundamental forces of nature. One of the other places that we're going is the search for the Higgs boson, which we've accomplished. We discovered it in 2013. It was announced in the summer of 13, but it was actually found on Pi Day in 13, also Einstein's birthday in 13. And so this is a very exciting piece of the puzzle of particle physics. The Higgs boson was a theoretical particle that explained why some particles are able to have no mass and why others have tremendous amounts of mass. And if you want to know more about how a Higgs boson works, I am not the person to ask. You want to talk to a particle physicist or a high energy physicist for that one. One of the other things that we're doing is producing antihydrogen out at CERN, and hoping to observe that while an electron orbits a proton in a hydrogen, we're hoping to see a positron orbit an antiproton in the exact opposite direction. Everybody be wowed by this skill right now. Oh yeah. But anyway, that's what we're expecting to see when we make antihydrogen at CERN. We're also constantly looking at cosmic rays and trying to look at things going back as early as the Big Bang to try to understand how the universe formed and came together and how we got all these tiny particles. What else is going on? We've got the ATLAS and the LHC projects going on out at CERN, which are huge particle accelerators that are operating at tera electron volts of energy and colliding particles to see what emerges. This is where we found the Higgs boson. Very exciting. If you would like to learn more about what's going on in particle physics, this presentation is in the Dropbox and the links are active. They will take you to different things that will help you to explore and understand more about particle physics in general. And to finish up, I'd like to leave you with two more quotes from Enrico Fermi. There are two possible outcomes. If the result confirms the hypothesis, you've made a measurement. If the result is contrary to the hypothesis, you've made a discovery. And it's no good to try to stop knowledge from going forward. Ignorance is never better than knowledge. So I hope that this presentation has confused you, but on a higher level. Thank you.